Hi students, today we're going to talk about intermolecular forces. So far we have been talking about intramolecular forces. Your intramolecular forces are these in between the bonds. They're the ionic and covalent bonds. Another way I could show this to you is if I were to draw like a Lewis structure. This right there is your intramolecular force. In that case, it's a covalent bond because it's between nonmetals. So those are between your ionic and your covalent. When ionic compounds melt, they are breaking ionic bonds. And since intramolecular forces are a really strong force, that's why they have really high melting points. It takes a lot of energy to break those bonds, which is why you need why they have a high melting point. Intermolecular forces, on the other hand, are the ones that are between two molecules. It's an attraction between the two molecules. It's not a bond. It's just an attraction. Think of magnets. It's an attraction between two molecules. It's much weaker. When covalent compounds melt or boil, their intermolecular forces break, and that explains their low melting points. So we're going to talk about types of intermolecular forces today. So looking at there are three types of intermolecular forces that you are going to need to know. The first type is London dispersion forces. London dispersion forces is something that all covalent compounds have, so no matter what, a covalent compound has London dispersion forces. And it's an attraction. So it's an attraction between two instantaneous dipoles caused by an imbalance of electrons. So all molecules have electrons, and those electrons are moving around. And so it's kind of hard to explain because you can't see what's going on. So I'm going to kind of draw a picture. What's going on is in a London dispersion force, let's say you have two molecules here, or I have one molecule here. And those electrons, remember those electrons can move around. And let's say at one point, those electrons start to, I'm going to erase these, and let's say the electrons start to burn instantaneous, and it only happens like that. So it's very quick that for one reason or another, all the electrons will gather up on one side of that molecule. Then what will happen if there's a molecule right next to it? Well, electrons don't like to be around each other, and this only happens for a split second. But because of that, the molecule right next to it, the electrons that are in this molecule are going to shift, and they're going to start to gather up away from those electrons because of the fact that they don't like to be around electrons. So because of that, electrons are negative. This side is going to be slightly negative. This side will be slightly positive. It forced the molecule right next to it to have a slightly positive side and a slightly negative side on that side, and then there's an attraction between the two. And it only happens for a split second. This is the weakest type of intermolecular force because it only happens for a split second and then it can go away. The big thing to note here for your London dispersion forces is that the strength increases as the total number of electrons increase. And we're not talking about valence electrons, we're talking about total electrons. And we'll have an example like that. Dipole-dipole forces. These are attractions between two permanent dipoles. These are for polar molecules. So HCl is a polar molecule. If you have two HCl molecules right next to each other, they are going to have an attraction between the two molecules because of the fact that electronegativity difference between the two. Your chlorine is slightly negative. It hogs the electrons. The hydrogen is slightly positive. It doesn't hug the electrons. And so there's an attraction between those two because this one has more electrons and this one does not. H bonding is just a special type of dipole-dipole forces. And it is an attraction between molecules with NH, OH, or FH. I kind of say hydrogen bonds want to have FON, and so that's where we get the F, O, and N. Do realize that this is not a chemical bond. It's very similar to this between attraction between the two. It's just that because nitrogen, oxygen, and fluorine are so electronegative, they hog the electrons a lot more than other types of atoms, and so they're stronger than just the regular dipole-dipole. Okay, we're almost to examples. So determining the types of intermolecular forces. You start with the Lewis structure, okay? And then if they are nonpolar, they're only going to have London dispersion forces. If they're polar and it doesn't contain HN, HO, or HF, it's going to be London dispersion forces and dipole-dipole. Because remember, every single type of covalent compound has London dispersion forces. And then if it contains HN, HO, or HF, then it's going to be LDF and H bond. Your strength of your intermolecular forces increases to the right, the stronger their IMF, the higher the melting point, and the higher the boiling point. So over here is stronger than over here. So I have two examples that we're going to go through. So looking at these, we're going to determine if they're polar or nonpolar first. So remember, you have a diatomic, and diatomics, if you have the same type of atom, it is going to be nonpolar. In this structure, we don't have a center atom, but because if you're thinking like maybe carbon is the center atom, you can kind of view it that way. If you're looking at this, well, it's not symmetrical all the way around, so this one is going to be polar. So now let's figure out the intermolecular forces using that chart. Looking above, N2 is nonpolar, so it's only going to have LDF. And then your other one is polar. It's polar, so we need to figure out, does it have an HN, HO, or HF? I do see an HOH, HO bond right there. And so it will have, we have an HO, so it's going to be LDF and H bond. Okay, which is going to have a higher melting point and why? Well, your strength of intermolecular forces increases to the right, so that means this one is going to be stronger than the one that's just LDF over here. And so this one's stronger, which means it has the higher melting point and higher boiling point. So that means it will be your, that CH3OH will have the higher melting point, and that's because it has stronger IMFs, or intermolecular forces. And our last example. You should pause and see if at least you can do the first two rows yourself, and then we're going to talk together about the other ones. Okay, I hope you paused. Looking at this structure, CCl4 is nonpolar. It is symmetrical all the way around. There's no lone pairs on the central atom. And CBr4 is nonpolar. So they're both nonpolar. If you remember from the chart above, nonpolar only has London dispersion forces. Okay, if you're comparing and they only have London dispersion forces, you want to be using the fact that your strength increases with the total number of electrons. So we want to actually look at the periodic table and see how many electrons they have. Do I have a periodic table? I do have a periodic table. Hopefully, there we go. So we had carbon. Carbon has 6 total valence electrons. We had chlorine, which has 17, and bromine that has 35. Okay, so I'm going to go write all of those down. Where did I put those all? I am in this one. Okay. So I said carbon has 6, chlorine has 17, and bromine has 35. Well, we have 1 carbon in this one plus 4 chlorines. So that would give me 74 total electrons. And in this one, I have 1 carbon plus 4 bromine. So that gives me 146 electrons. So because the CBr4 has more electrons, this will have the stronger intermolecular force due to more electrons, and will have stronger melting point.